semester, we have fixed bias example. So let me copy that inside the collaboration space. Copy. Then we have emitter stabilized bias example. We'll do more, not just these two. We'll do more of these today. So let's go to our collaboration space, see what we have brought in. This state is no longer valid. So what I'll do is erase everything first. We can start again from the beginning. This is also a worked out example in your textbook. I think it's example, what is it? 4.1, chapter 4. I hope everyone can see. A few things we need to solve for this circuit, which means I have to give you which parameters that we would like to solve. You see, definitely you need the base current. So let's solve for the base current, IB. And then find, what else should we find? We should find the output collector current, IC. We should find VCE. In addition, I would like to ask you some other VC, VE, maybe VB as well. And pick a few students. All right. What else you should know here is the beta value of 50. This is the example of a fixed bias. You have resistors on base and collector terminal, but you do not have on the emitter terminal. So that's a fixed bias one. I will pick one student randomly. Is silicon here?
Yes, teacher.
Silicon, you solve the first one, IB. So let me
Okay.
put for you number 1. Wisalu.
Yes,อาจารย์
Wisalu, solve IC.
โอเคครับ
Yu Cheng.
Yes, teacher.
Yu Cheng, you are number 3, VCE.
Number
Then,
3.
yeah, Sheshehan, number 4, VC.
Okay, then.
Number 5 is for Patompong. Tumsu will solve for number 6. Everyone else, you are free to work on the same problem. And after a few moments have passed, maybe 1 or 2 minutes, I will also guide you. Now I'm giving you time to get familiar. You can look at your own lecture slide and see what the formula is. In the exam, formula sheet is given, so you don't have to worry much for that one. This is chapter 4, example, I believe it's example 4.1. What is it? It's 4.1. So in order to solve the base current IB, if I draw for you the path of current on the input loop, the KVL path, VCC minus IB RB minus VBE equals 0. Do not forget the VBE. Even though it's not in the circuit, you should always take the voltage drop VBE at the BE junction. For the silicon, we assume it's a silicon transistor. The value is 0.7 volt. What would be the value of IB using this KVL loop? Are you okay solving the problem? I'm not looking at the formula sheet. I just look at the path. So what is IB then? If you want to express in microamperes, what is the value of IB? Let me know
Teacher,
when you're
I
done.
got IB. I got 0.0475 milliamp.
So 0.047 milliamp.
Yeah,
If you want to express in
0.04.
microamp, it will be 47 microamp around.
Yeah, 47 milliamp.
If I do exactly in calculator, it's 12 minus 0.7 divided by 240 kilo ohm.
Oh, yes, plus 0.6.
I got 48.083. I'll just write 48.08 micro. After silicon, we have Visalut. The value of IC. How are you going to calculate the value of IC?
This is beta time IB.
Yeah, very good. If you take the beta and multiply by IB, you're going to get IC equals beta IB. So
2000 2350 ครับอาจารย์
what is your unit? Are you going to express in ampere or milliampere? It's better to express in milliampere. Maybe you're missing 10 power negative 6. You cannot have 2000 ampere. Not even 2000 milliamp. You said 2350. It is around 2.35 milliamp.
yes 2.35
But you
milliamp
forgot to multiply with 10 power negative 6.
โอเคครับ
If you give me answer 2300, you're not going to get marked for that one in the quiz or exam.
โอเค sir
Who is doing VCE? Yu Cheng? Mr. Yu Cheng?
Yes, teacher.
VCE, have you solved for VCE?
Wait a minute, teacher. I still doing.
While you are doing, let me draw the outer loop. VCC minus ICRC minus VCE equals 0. So you need to know the value of IC. That's why everyone should calculate everything. 12 minus IC times RC, that is your VCE.
Yes, I know, teacher. Today I forget to use the engineer calculator. I use a phone calculator, so it's
Okay,
maybe
so
I
you're
have
gonna be a
some.
bit slow. Let me give you the answer.
Yes.
I get 6.82 milliamp. The book says 6.83, but we are close.
Okay, I will check.
Sorry, not milliamp, it's volts. What am I saying? 6.82 volts. Shishihan, you
Yes,
are
Ajahn.
number 4 on the list. Can you find VC in this circuit?
VC equals to VCE.
Yes, VC equals to VCE. VC is the point exactly here. VC, it is the voltage drop, VCC minus ICRC. That's VC. Why VCE and VC same? Because the E is directly on the ground. You can say VC minus VE. You can write as VCE. So you can see VC is VCE plus VE. What is VE? Patompong, what is VE? Have you solved?
Is it zero?
VE is 0. Right, you're right. VE is here. Emitter connected to the ground, 0 volts. Kumsu. What about VB?
VB is VBE plus VE.
Correct. VBE plus VE. Okay, yeah. Using double subscript, you can write that. So what is the final value?
0.
What is the value of VBE?
VBE is 0.
VBE is not 0. I told you already. What is VBE for this transistor?
Is it 12 volt?
No, VBE is 0.7 volts. And VE is 0, therefore you have 0.7 volts. Silicon, we assume it's silicon. From base to emitter, you always have to take VBE equals 0.7. I explained in the previous class. You have another way of finding VB if you want. You can say VB is right here, which is VCC minus IBRB. You can put all the value in the equation. You will see it's 0.7008, means 0.7. VB is 0.7 volt. Now, I want to ask you, what will be VBC? If I ask, what is the voltage between base and collector? How can we find out? VB minus VC. How much do you get?
Negative 6.12 1.
You get a negative voltage, 6.12. This is a transistor that is operating in normal range. When it's operating in normal range, the base to collector junction, base to emitter junction will be a positive value. If you want to check your transistor whether or not it's working, you will see for a normal operating BJT, VBE will be positive. If you put the voltmeter probe, the red probe on B and the black probe on C, VBC, you should get a negative volt. So this is operating in the normal operating condition. That's one way to check whether or not a transistor is working properly. After Kung Su, next problem, we will start with the next student. For that, we have emitter stabilized bias. Let's just erase some old information. It is not even worked out. Okay. I'll have to remove the date. The date here is no longer relevant, but it doesn't allow me to do anything. What's happening? How do I delete it? The delete button is not working. It should work now. Okay. Let me again enlarge the picture. We have a few things to solve. 7 parameters. Mr. Martin will be A, IB. Martin, present.
Yes, Ajahn.
Korawit. Where is Korawit? Are you present? Korawit is present in the class. Can you hear us? Korawit will do number 2. I see you online. So not responding is not, I can notice who is here. Which are you?
Yes.
Number 3. Jimma will do part D, BC.
Okay, sir.
Chuanyuan,
Hello.
Yes.
you will be doing part E, VE. Satawat, part F. Is Satawat present?
Yes, Ajahn.
You are doing VB. And the last one will be Mr. Yapeng Wang.
Yes, teacher.
I'm gonna do number G.
Okay.
Of course, everybody have to solve everything by yourself.
I'm gonna be here.
Kulawit,
Yes.
which one did I ask for, Kulawit?
Is that B, right?
Yes, part B. About it, you can also look back to your slide notes. If you need the formula, you can use the formula. Maybe it's hard to memorize.
Sorry, so RB is 430 kilo ohm, right? And
RB is 430 kilo ohms. So let me also draw for you. That is the base terminal. That resistor is RB. This is collector RC. This is an emitter resistor now. Now we have a different circuit, RE. First of all, when you do DC analysis, capacitor is open. Forget about the capacitor. Think that there is no capacitor, there is no input signal AC, no output AC. You just concern yourself with the DC analysis. Inside loop, input loop, VCC. VCC is 20 volt here. This is VCC. VCC minus IBRB minus VBE minus IERE equals 0. But then IE is IC plus IB, and IC you can say beta plus 1. IE is IC plus IB. The equation is simplified how? The multiplier is beta plus 1 times IB, that is IE. IE equals beta plus 1 times IB. Therefore, the equation is VCC for IB. The equation is VCC minus VBE divided by RB plus, you have to multiply RE with beta plus 1, 51 times RE.
Sorry, Ajahn, can you please repeat that again for IB?
VCC minus VBE divided by RB plus beta plus 1 in the bracket multiplied by RE. So you're basically taking 20 minus 0.7 divided by 430 kilo ohm plus RE is here 1 kilo ohm times 51 because beta is 50. If you do everything properly, my calculation is 40.12 microamp. This is micro mu. What is IC then? Once you find IB, what is IC? Have you found IC? Whoever is doing IC?
Yes, this is 2.06 milliamp.
Point
2.006
you can
milliamp.
say 2.01 then. 2.01 milli. For VCE, you have to look at the outer loop. VCC minus ICRC minus VCE. Now you have minus IERE equals 0, but it is possible to do the approximation. IC approximately same as IE, it will not change the answer much. So VCE will be VCC minus IC times RC plus RE. 20 minus 2.01 milliamp.
13.97.
Okay, times 2 plus 1, 3 kilo ohm. It is 13.97 volts, correct. The next question is VC. How much is VC? Just at this point is VC.
15.98.
So it is VCC minus ICRC. You just stop here. 15.98. 20 minus IC times RC. 15.98. Now what is VE now? The next one is VE. How will you find VE? You can say VE equals VC minus VCE. That will be VE. Or you can say VE equals IERE. When I approximate IE as IC, you can write VE same as approximately ICRE. VE is here. So from that point to ground, the current flowing approximately same as IC multiplied by RE, and the bottom is ground.
It's 2.01 volt.
2.01 volt. Are you on campus? I hear a bell sound.
Yes.
They're still ringing the bell?
Yes, it's still.
Okay. VB. We can find VB next. How do we find VB? You can write VBE plus VE if you want to use this double subscript notation. Or you can use another equation in the loop. Slightly different if you take the loop, but the answer should be close. If you take 20 minus IBRB, you're gonna get 2.77. If you take VBE plus VE, you will get 2.71. Slight difference. So if you take VB equals VBE plus VE, this plus that, you should get 2.71 volt. 0.7 plus 2.1 is 2.71. Finally, the last person is doing VBC. What is VBC?
Minus 13.27.
So it is reverse biased with 13.27 volts. The last one is minus 13.27 as required. From base to collector, it has to be reverse biased, 13.27. You may even write 13.3. So that is the example with emitter stabilized bias. In my previous class, I showed you examples of how when the beta changes from 50 to 100, how the output voltage VCE and IC will change. For the case of fixed bias, there is a lot of change when beta changes, but for the case of emitter bias, there is change, but not as big as fixed bias. So the emitter stabilized is a bit more stable. I will bring you back to the lecture slide. I will take a quick break for the washroom, but we start from this slide now, voltage divider. Please have a look for about a minute and I'll be back. Okay, I've returned to my desk. Can you see voltage divider bias on your screen?
Yes, sir.
This one is even more stable than the emitter stabilized bias. That's why the slide starts with the comment that it is a very stable circuit. The output voltage and current are nearly independent of beta variation. Not fully, but nearly. Which means if you change the beta for temperature, you don't have to change it by yourself, it will change. The variation in output current and output voltage will be much less than both the fixed bias and the emitter stabilized bias. Beta is a temperature sensitive parameter. Normally IC and VCE will be dependent on beta. The voltage divider configuration gives us a circuit where currents and voltages are almost not affected by beta variation. There are two ways of analyzing this circuit. The first one is called the exact analysis, Thevenin equivalent circuit. How do you find Thevenin equivalent circuit? By circuit analysis. Does anyone remember from your circuit class? How do you find the Thevenin equivalent? If you look back from the load side, and for Thevenin equivalent resistance, if you want to calculate the Thevenin equivalent, all the DC have to be grounded. So this VCC is grounded, looking from the load side to the source side. I draw a vertical line. The left of the yellow line is source, the right side is load. We look at the source, find the equivalent resistance of the source. What do you see? R1 when goes to ground, R1 comes here. We are not worried about capacitor now, we are DC analysis. This becomes R1. When VCC is killed, you see two parallel resistors, R1 and R2, that is on your source side. So RTH, the Thevenin equivalent circuit in the inside the source network is R1, R2 divided by R1 plus R2. That is Thevenin equivalent resistance. Now, you also need to find the equivalent Thevenin voltage. How? After you find the Thevenin equivalent resistance, make everything the same now. You have to put back the battery on the source circuit. So what do you have? VCC. What does it see? VCC times R2. This is a voltage divider equation. At this point, this is the Thevenin equivalent voltage E. E of TH is the Thevenin equivalent voltage. It is not called VB, not yet. There is another way of analysis where you can say it is VB. A bit clearly. How do I zoom? The zoom button is not here. What happened? Is it zoom in, zoom out? Oh, here. It doesn't zoom. View, zoom. Zoom to this area. The toolbar is gone. Okay, I have to look at it later. Is there any other way? Any shortcut? View, page display, zoom, dynamic zoom? Yeah. So at this point, it is Thevenin equivalent voltage, ETH. If you put the DC source back in the circuit, at this point, it's VCC times R2 divided by R1 plus R2. So the circuit to the left of the load is simplified as in following. You have an equivalent voltage source, ETH. You have equivalent resistor, RTH. That's the source network. And then what do you have? This is load. We have to solve for the Kirchhoff's voltage loop. What do you get? ETH minus IB times RTH minus VBE minus IERE equals 0. That is this equation. I hope you can see the equation. What is IB then? ETH minus VBE divided by RTH plus beta plus 1 RE. Why IE equals IC plus IB? From that we got beta plus 1. Clear? So IE equals IB plus IC and IC equals beta IB. So if you simplify, everything can be expressed in terms of IB and you get this equation. Also, the equation is given where? On the formula sheet that you will get during the exam. What about the outer loop? Let's go to the outer loop. When the current is flowing, VCC minus ICRC minus VCE, because there's a C to E drop, minus IERE equals 0. If you take IE approximately same as IC, you can write VCC minus IC times RC plus RE minus VCE equals 0. From that, you get the equation for VCE. Any questions? Are there questions? Can we move on to the next part?
Yes. Right,
So
teacher.
this analysis is called exact analysis or Thevenin analysis.
Teacher,
Yes.
I want to know where do we find like R1 and R2?
R1 and R2 in the problem is given. The original circuit is given.
Oh, okay.
All the values are given. You have to change to Thevenin equivalent resistance. In the exam or quiz anywhere, if you are given a voltage divider circuit, you must read the question carefully. What type of analysis I'm asking for?
So teacher, the unit will be like Some of the current will be like MA, right? For the
Some
unit.
will be MA, some can be microamp. IB can be microamp or a small milliamp.
Okay.
So this is
What,
exact analysis, yes?
what about the resistance? What will be the unit?
Resistance is in the range of kilo ohm, small to large kilo ohms, but we will do problem today. We will do exercise.
Got it.
Exact analysis, it asks exact analysis or Thevenin analysis you have to do by this way. The first step is find RTH, find ETH. If you do not find RTH or ETH, you cannot solve this equation IB. As you can see, this equation needs the Thevenin voltage and Thevenin resistor. There is another analysis technique which is called approximate analysis. You don't have to go through all these steps to find IB. You can do some exact analysis, but some condition has to be met. Approximate analysis. Let's say IB is, okay, the current flowing through R1, if we call this I1, right? And the current flowing through resistor R2, if you call this I2. And then you have a current also going to the base. When IB is so small that it is almost negligible compared to I1, which means all the current coming from the source, just a tiny bit is going to IB, but the rest can go to R2, which means you can approximate I1 and I2 as the same current, only a little bit of loss from the base current. In that case, you can use this equation VB, which is the voltage at point B, the base. VB will be VCC R2 R1 plus R2. It happens to be the same voltage as the Thevenin equivalent. At this point, you are calculating the voltage using voltage divider equation, VCC R2 over R1 plus R2. And then we are not calculating IB in the beginning. You must satisfy this condition. Beta multiplied by RE from all the resistor values which are given in the problem, the beta is also given. If you multiply beta with RE and it is greater than 10 times R2, only then you can do this analysis. Otherwise, you cannot use this analysis. The answers will be wrong. That's the condition you have to satisfy. If the condition is satisfied, you can just say IE is VE over RE, Ohm's law. VE, you can say VB minus VBE. That is correct. I think yes. You will know VB from the first equation. VBE is 0.7, so you can find VE. From VE, you can find IE because RE will be given. Then what will you do? IE approximately same as IC. You can find beta. You can find IB because beta will be given. IC equals beta IB. So IB is IC divided by beta. You can find IB without solving the KVL. On the outer side is the same, VCC minus ICRC minus, I'll say ICRE because IC same as IE minus B. This whole loop, VCC minus ICRC minus VCE minus ICRE equals 0. Therefore, this is the equation for VCE. This equation is the output equation, the load line equation. If you want to find the cutoff point, when IC is 0, VCE equals VCC. When VCE is 0, the saturation current IC is VCC divided by RC plus RE. From that equation. So you can put one value to 0 and you can find the other extreme parameter. Once you find the cutoff equation, what do? You draw the load line, and then from the characteristic graph, you can find the characteristic graph. The base current intersects, you can find the Q point. Do we have an example here? I'm going to go a bit ahead, but I'll come back. No, we have to do in the class. The voltage divider bias. Let's look at an example, if we can do an example. So I'm going to go back to the content library and try to get an example for you. There's a voltage divider bias, which was taught in the previous class. Let me copy that for you. So I'm again on the collaboration space. For some reason, the picture does not come in. I don't see any picture. Oh, the picture is loading now. Okay, no problem. Let it load. Can you see the picture now?
Yes, sir, we can see it.
So determine the DC bias voltage, VCE, and current IC for the voltage divider configuration shown. It does not say whether we should do the exact analysis or approximate analysis. So we can do the exact analysis first. Is beta times RE greater than 10R2? Beta times RE. RE is 1.5 kilo ohm. $150,000. What is 10R2? 39,000. No, beta RE is not greater than 10R2, so we cannot do the approximate analysis. We have to do the exact analysis. First, find ETH or RTH. Let's find RTH for exact analysis. What will it be? You can tell me. Remember, RTH is R1 parallel R2. This is R1, R2. You have RC, and you have, this is RE. Capacitor, don't worry about it. We can forget now. What is RTH? 39 kilo ohm parallel with 3.9. 3.545. What should I write? 3.55. Let's call it 3.55 kilo ohm. Can you follow the step? Are you following the step?
Yes,
Everyone? The next, you have to find ETH, the Thevenin voltage for the source side. It is VCC-R2. I'm not going to write the equation. VCC-R2 divided by R1 plus R2. So 22 divided by 3900. Sorry, 22 multiplied by 3900 divided by 39,000 plus 3900. I think I get exactly 2 volts. ETH is 2 volts. 2 V. It is asking me to find IC VCE. Without IB, we cannot go any further. So we need to find next is IB. Now I can write the equation for you if you are confused. It is ETH minus VBE. What do I say the value of VBE for this chapter? Take 0.7. If I don't give you any other information, it's 0.7. RTH plus what? Beta, add 1 in the bracket, and you have RE. That's the equation. Can we solve? What will be the value? 2 minus 0.7?
Teacher,
Yeah.
I want to know where is VCC?
VCC is the DC bias. So VCC is right here. VCC is always the DC source.
Oh, okay.
This one. This is VCC.
Okay, got it.
So ETH is 2 volt. 2 minus 0.7 divided by 3.55 kilo ohm, and then plus, it will be 101 times 1.5 kilo ohm. What's the value?
I got 8.38 microamp.
8.38 microamp or 8.4 microamp. Yeah, we can say 8.38. No problem. 8.38 microamp. 8.38 mu a micro ampere. And then what is IC? Now this is IBQ. This is the operating base current because you established it already. So IC, what is IC or ICQ? You can say. We just multiply IB with beta. You multiply this with 100, you get 0.838 milliamp, isn't it? Or you can say 0.84 milliamp. It is beta times IB. Well, then, what is the other one being asked? VCE. VCE is very straightforward. Again, let me draw the loop. VCC minus ICRC minus VCE minus ICRE equals 0. Therefore, VCE is VCC minus IC times, you add RE and RC in the bracket. 22 minus 0.84 milliamp multiplied by what is the total resistance? 10K and 1.5 is 11.5 kilo ohm. 22 minus 0.84 milli and kilo, they cancel out. So you can just say 0.84 times 11.5. The voltage VCE, you should get about 12.34 volts. This is the VCE equation. Minus IC times RC plus RE. That is the VCE. I got 12.34 volts. I think that is correct. This is the exact analysis. If you found the question is asking approximate, you can do approximate, otherwise not. If you try to do approximate analysis with this circuit, you're going to get values which are totally wrong, because the condition beta RE is not greater than 10 R2. You cannot find that. All right. Any questions?
No, sir.
One more bias we can look at. Let's go back to this slide. So this one is already covered. DC bias with voltage feedback. The proper name for it is collector feedback. It may look like the emitter bias, but it is not the emitter bias. If you look closely in the circuit, let's see what it looks like. If you have a fixed bias, there's a VCC and then base resistor, come back to base, and then you have, for emitter stabilizer, you have RE, RC. Now what's happening? The connection to the base is not coming from VCC directly. Where is it coming from? After collector terminal C, you have a feedback resistor. That's why it is written RF. And then it goes to base. If you think the main current coming in is IC prime, it separates as IC and IB, or you can say IF. At this node, the current is split as a base current, which is much smaller, and then it goes to the transistor output side. If this is milliamp, that is microamp, you can say approximately IC equals IC prime, ignoring the IB part. If you want to further improve the stability of the circuit, you can take collector terminal, add a feedback resistor, and feed back to base. In this case, the operating point is only slightly depending on the beta. So the output current and voltage swing will be even less. The worst one is fixed bias. The next one is emitter stabilized, slightly better. Voltage divider feedback, much better than emitter stabilized. And this one is also equal or better than the voltage divider. We can also solve the input and output loop. If I look, VCC minus IC prime RC minus IB RF minus VBE minus IE RE equals 0. That's quite a lot. I admit that. See, so many terms. VCC minus IC prime RC minus IB RF minus VBE minus IE RE is 0. When IB is much less than IC, you see from the loop, IC prime equals IC plus IB. So if we ignore IB, IC prime is same as IC. So in this equation, then instead of IC prime, if you write IC and you express in terms of beta, like IC equals beta IB, and then you take again IE approximately same as IC, you will get an equation that is more friendly. In order to find IB, you get VCC minus VBE divided by RF. Now we don't have RB, we have RF, feedback, plus beta times RC plus RE. This equation is also on the formula sheet. You don't have to memorize it. You just understand how we derive the equation. Next is to find the outer loop, the collector emitter loop. What do we have in the collector emitter loop? Clear up this picture. VCC minus IC prime RC minus VCE minus IE RE equals 0. Now what are the approximations? IC prime is same as IC, so we can write VCC minus IC RC minus VCE minus IC RE. We always approximate IE as IC. That is the outer loop. Solving, you get this equation, which is similar to so many other you saw in the beginning. VCE equals VCC minus IC times the two resistors in series. So what is the cutoff voltage? If at the cutoff there is no current, means VCE equals VCC. At the saturation, VCE is 0, there is a lot of current. IC will be VCC divided by RC plus RE. We have done this so many times before. Just set current to 0, find the voltage, and then set the output voltage to 0, find the current, cutoff, and saturation. You can then solve the problem just like the other bias circuits. Maybe we do the example today, but maybe on the next day for the collector feedback. But many semester I missed this part, the transistor switching circuit, and then I missed an AND OR gate. So for this semester, let me teach you this one. Have a close look at the input and output. So what are you noticing? When the input is high, what is the output?
It is 0.
Yes. Input is 5 volt, output is 0. Input is 0, output is high, 5 volt. This circuit, there is a name for this circuit. It is called an inverter. If you want to take like a signal and then totally flip it around, do the opposite output, this is an inverter. This is a switching application. We can analyze this circuit as well. Let's say input signal, input is applied here, Vi. Input is not VCC, remember. Input is what? Here, the signal is here, there will be capacitor and so on. Now, we are talking about DC, so there is no capacitor. VCC is not an input. VCC is the biasing that you need to turn on the amplifier. Without VCC, the amplifier does not do power transfer. When Vi is 0, what happens in the circuit? There is no current flow here, correct? Will there be any current, IB? No current. So if there is no IB, is there any IC? When IB is 0, what is IC? IC is also 0. When there is no base current, there is no collector current. If IC is 0, if you try to take the output VC here at this point, what will be the voltage value it sees? VCC minus ICRC. Now IC is 0. So what does it say? It will see directly the value of VCC. The probe will directly sense the input from VCC. That's why when Vi is 0, you have 5 volts. Digital logic, if you think of digital logic, a 5 volt level is high. So you see high volt. Second case, you have an input, Vi is 5 volt. Now Vi is 5 volt. When you input, there is a current flowing in the base, from base to emitter. What is IB? See, the base is not connected with VCCs. You have to solve IB from right here. Is the IB connected with VCC? No. So the loop is not on the upper left. The loop is on the left hand side. You can say Vi minus IBRB minus VBE equals 0. That is the KVL loop of the left hand side. Therefore, IB is Vi minus VBE divided by RB. 5 minus 0.7. You get 4.3 volts. You divide by 68 kilo ohm. What is the answer? What is the answer? 4.3 over 68K. 63 microampere. IB is 63 microampere. Can everyone follow what I'm saying? Does everyone understand how IB is calculated now?
Yes, sir. I guess so.
5 minus 0.7 divided by 68K, 63 microamp. If you have IB, you can calculate IC. IC is beta IB. What is beta? Some spec sheets, instead of beta, they write H sub FE. That is beta. 125. Multiply 63 microamp with 125, you will get 7.9 milliamp. No, not 7.9. Let's do 100 to make it. Let's do 100 to make it even. 63 microamp. If you multiply by 100, you will get 6.3 milliamp. Let's call it 100. Because with this example, you get a negative voltage. So I want 100. What is VC now? VCC minus ICRC. If you take 5 minus 6.3 milliamp multiplied by 0.82K, you get a negative voltage or a low voltage, I think. What do you get? I think you get a negative one. So VCC have to be large or RC has to be small. So the idea is now the value you get for VC is small enough to be logic levels low. When you have high, there's a problem with this circuit design. The RC value should be less, or VCC should be high, or beta should be lower than this. If you take 90, maybe you will get a proper value. Maybe slightly over 0 volt, but it doesn't even go to 1 volt. So this is the reason why when VI is 0, you're going to get a full VC, same as VCC. When there's an input VI, because of IB and IC now, the voltage drop brings the VC down close to 0. This is called an inverter, switching circuit. You can also use, just like I showed with the diode, we can also use logic gates by transistor. This is the truth table on the right hand side. What gate is this? The first one. The first table.
OR gate.
It's an OR gate. Both 0, you get 0, but any of them becomes 1, you will always get 1. And the second truth table is AND gate. In order to get high output from an AND gate, you must have both as 1. If even one of them becomes 0, you don't get an output. So OR Boolean logic is given by A plus B, and is A dot B. C is the output. See what happens on the left hand side. Let's say Q1 is 0, transistor off, Q2 is 0. Are there any current? No, because from VCC, it does not pass through here. The circuit is open. It does not pass through here. It stops right there. No output. Let's make one of the transistors on. Which one should I turn on? Let's turn off this one. Let's close this transistor. Now you get a value. I think if you think VCE as short circuit, then you get the full value of VCC. 5 volt, high level 1. Turn on the first transistor, turn off the second one. There's a path through the first transistor. Again, you're gonna get an output. And of course, when both are on, have current going through both parallel paths, you'll get a value. That is OR gate. Look at the right-hand side circuit. AND gate. Let's turn off both transistors. Q1 open circuit, Q2 open circuit. Can the current pass through here? No. C is 0. Now I will open Q1 and then turn on Q2. Again, the current is already blocked. There is no path to flow. You will not get any output. Close the path of Q1, turn it on, but Q2 is off. The current will stop at here. At C point, there is no output. Finally, make both of them on. Now there is a full path. You will sense a high output on C. That is logic gate AND using transistor. So the way you arrange the transistors, you can get AND or two simple gate. Where is this coming from? Switching circuit calculation. Okay, you know saturation is VCC over RC. I think in this case, where is the switching circuit? Here, VCC over RC. In order to ensure saturation, the base current has to be greater than saturation current divided by the DC level beta value. Saturation resistance is the VCE at saturation over IC. And then for the cutoff, you take VCE equals VCC. And what is the cutoff current? ICEO means the current from collector to emitter when the terminal is open. They will be so small, if you divide something by so small, almost infinity, very high. For the cutoff, high resistance, which makes sense, it will not allow current to flow. As you can see, the cutoff is here. What is the value of IC at the cutoff? Almost 0. For saturation, very low resistance. That's why you can get a high current for saturation. What do we have next? Switching time. We're going to study in the next class with an example of collector feedback. We are a bit ahead of our schedule, so I will not go any further. Next class, we do this example. Here's the circuit of DC bias with voltage feedback. I'll find a collector feedback example, solve in the class. We will explain the transistor on-off time, but most importantly, we will start AC analysis. Until now, we did DC analysis. We did not worry about capacitor and signal. Now you have to do AC analysis by a certain way. What do? Capacitor, you have to take into account. For DC, you have to kill the source. We'll study in the next class. I will now take the attendance. Mr. Balan?
Yes, sir.
Tirawut? Napatra?
Yes.
Takon?
Yes.
Rajay?
Yes, Ajahn.
Sonikan? Sonikan present? Michelle?
Yes, Ajahn.
Phil?
Present, sir.
Silicon?
Present.
We salute.
Yes.
Cheng is present. Sheshehang? Where is Sheshehang?
อาจารย์คะ
Yes.
ช่วงนี้การพรีเซนต์ค่ะ
Okay. Patompong?
ปฐมพงษ์เฮียครับ
Kungsu present. Martin present. Kolawit is present. Pichayut, you are present? Yes.
Yes.
Jimma and Xuanyuan are present. Satawat is present. Yapeng? Where is Yapeng? Present.
Yes, teacher.
Seni?
Yes, present.
Sidipok?
Yes, present.
V2.
Yes, teacher.
San An,
Yes.
Waramet,
Yes.
Nabawan,
Present.
Natapop,
Yes, present.
Warapat,
Present, sir.
Nataya,
Yes, teacher.
Chayapon,
Yes, sir.
Komchan,
Yes, Kumchat here.
Kiradon,
Yes, I'm here.
Itsanapong,
I'm here, teacher.
Atitaya,
Yes.
Tasi,
Yes.
Sukaina,
Yes, teacher.
Sirin,
Yes, teacher.
Minluin U. Let me see. He's from 555 section. Someday he's here, someday not. I'm missing one student, I think.
Teacher Yuchen.
Yes, Yucheng, I got it. Min Luin U was not present today.
Ajahn, say.
Yeah, Sisi Han. I got everyone except Min Luin U. I'll see you again on Thursday. We will continue the BJT chapter.